So today I'm reading Causal Discovery from Incomplete Data, a deep learning approach from MIT Abstract. As systems are getting more autonomous with the development of artificial intelligence, it is important to discover the causal knowledge from observational sensory input. By encoding a series of cause-effect relations between events, causal networks can facilitate the prediction of effects from given action and analyze their underlying data generation mechanism. However, missing data are ubiquitous in practical scenarios. Directly performing existing causal discovery algorithms on partially observed data may lead to incorrect inference. To alleviate this issue, we propose a deep learning framework dubbed Imputated Causal Learning (ICL) to perform iterative missing data imputation and causal structure discovery. Through extensive simulations on both synthetic and real data, we show that ICL can outperform state-of-the-art methods under different missing data mechanisms. Introduction. Analyzing causality is a fundamental problem to infer the causal mechanism from observed data. Usually, causal relations among variables are described using directed acyclic graph with nodes representing variables and edges indicating probabilistic relations among them. Learning such causal networks has proven useful in various applications, ranging from smart cities to healthcare. For example, knowledge of causal structure is helpful for analyzing relations among different business entities and supporting business decisions. 2. Necessary in learning gene regulatory network and analyzing complex disease traits. 3. Important for visualizing causal attentions of self-driving cars and highlighted region where a highlighted region would causally influence the vehicle steering control. In short, the discovered causal networks enable accurate decision making, robust uncertainty inference, reliable fault diagnosis, and efficient redundancy elimination. Previous works on causal discovery mainly focus on the complete data setting. They either try to learn the Bayesian network structure to estimate Markov properties or use the additive noise model for causal inference. However, causal discovery under missing data setting is still relatively underexplored. In practice, missing data is a common issue. The underlying missingness mechanism can be categorized into three basic types: missing at random, missing completely at random, and missing not at random. For example, sensors on the road intersections can record the traffic density, and traffic-related information will be transmitted to the roadside units. For traffic management in real time. In MAR, missingness is caused by fully observed variables. For example, when vehicle density is above a threshold, RSUs will get overloaded and fail to collect traffic data. Missing traffic data depends on the traffic density recorded by the sensor. MCAR is a specific case of MAR. The cause of missingness is purely random and does not depend on the variables of interest, such as the loss of traffic information. Traffic information happens by chance. In MNAR, missingness depends on either unobserved attributes or missing attribute itself. For example, the missingness of RSUs depend on traffic density detected by the sensor. Additionally, the sensor itself also introduces missing values. Some previous approaches handling missing data by directly deleting data entries with missing values, resulting in incomplete observation for a problem at hand. This data processing way may be satisfactory for a small portion of missing values, for example 5%, but could result in biased model in presence of larger missing proportions. In theory, MCAR and MAR conditions ensure the recoverability of underlying distributions from measured value alone, and do not require the prior assumption of how the data are missing. Therefore, feasible solution can be first performing imputation to recover missing entries, and then followed by causal discovery algorithms for knowledge representations from the recovered data. However, as will be discussed further, directly performed imputation could introduce incorrect causal relations. In this paper, we focus on causal discovery for observational data, as opposed to intervention experiments. Note that estimating the causal graph as a DAG in the NP-complete problem is an NP-complete problem, and the task becomes even more challenging under missing data condition. Causal discovery is an unsupervised learning problem, and the goal is to discover the data generation process in the form of causal graphs inspired by and motivated by recent successes of generative adversarial networks, GANs, and variational autoencoder. In learning high-dimensional distributions, in this work we use GAN and VAE to decompose this problem into subproblems, namely iterative imputation with causal skeleton learning, and identify individual parts of causal directions. In general, causal skeleton learning returns a reasonable network structure and offers a global view of how variables are dependent on each other, while causal direction identification provides a more accurate local view between the matched variable pairs. This complementary local and global view helps approximate the data generating process among all observed variables. Our contribution is threefold. We propose a deep learning framework called imputed causal learning for iterative missing data imputation and causal structure discovery, producing both imputed data and causal skeletons. We leverage the extra asymmetric cause and effect information within the dependent pair set in causal skeleton G. The causal directions in G then being enumerated in a pairwise way to uncover the underlying causal graph G. Through extensive simulations on both synthetic and publicly used real data, we show that under MCAR and MAR conditions, our proposed algorithm outperforms state-of-the-art baseline methods. So related work, causal discovery from complete data, methods for identifying causal relations from complete observation data usually fail in two categories. Usually fall into two categories. The first one exploits Markov properties of DAGs, and second one tries to leverage asymmetries between the variable pairs of functional causal model FCM. Constraint-based approach discovers conditional independence between variables of DAGs. Typical algorithms under this category include the PC algorithm, first causal inference, really fast causal inference, greedy equivalent search. Greedy equivalent search is a score-based approach. It performs structural learning with scoring criteria over the search space of the Markov equivalence class. The recent breakthrough makes the score-based method amenable with existing black box solvers. DAG GNN learns DAG structure using a graph neural network. Besides, hybrid approaches such as adaptively restricted greedy equivalent search ARGES, causal generative neural network, which combines ideas of constraint and score-based approach. They restrict the score-based search space with help of the conditional independence graph for either the computation efficiency or performance accuracy. Meanwhile, methods in the second category can be used to identify the causal directions, include linear non-Gaussian acyclic model, so and so on. So let's review this one once more. So the causal discovery from complete data. Constraint-based approach discovers conditional independence between variables of DAGs. Okay, and the score-based approach performs structure learning with scoring criteria over the search space of Markov equivalence class. Okay, interesting. And the contribution of this paper is to propose deep learning framework, leverage extra asymmetry in cause-effect information within dependence pair set in causal skeleton. The causal directions being enumerated in a pairwise way to uncover underlying causal graph. And through extensive simulations of both synthetic and publicly used real data, we show CAR and MAR conditions and outperform state of the art. Okay, let's continue. Causal discovery for incomplete data. Works related to causal discovery from incomplete data can be classified into two categories. One category attempt to discover causal structure using only available partial observations, and other aim at imputing all missing entries to recover the whole observation. Okay. List-wise deletion, test-wise deletion. Okay, let's continue. Imputed causal learning. On a high level, our model first takes incomplete observational data X as input and then simultaneously performs missing data imputation and structural learning to estimate both causal skeleton and recovered data. After that, pairwise causal direction identification is performed to orient the causal edges and uncover final underlying causal graph. Figure 1 shows an overview of our framework. The following subsections explain these two steps in detail. Okay, so they have missing mask, random noise, and real observations. They are all inputs that go to generator, while discriminator gets missing mask, and it also gets output of generator, which is passed through the imputation first. The discriminator then estimates mask, and the imputation also outputs to causal skeleton encoder, causal skeleton decoder. And then causal direction identification is performed. System architecture of our proposed ICL network, including three modules. We train module A and B to end-to-end manner for simultaneous imputation and causal skeleton learning. The results is used as an input of module C for the direct identification. Causal skeleton discovery from incomplete data. Problem formulation method overview. Equation 2 is corresponding. Okay, so under missing data condition, we assume confounders, unobserved direct common cause of two variables do not exist in the data input. This means that we can observe all variables, but some samples may be missed. Define incomplete version. Imputing. Note that unlike previous causal discovery approaches dealing with missing data, let's back up a little bit. We assume confounders do not exist in the data input. This means that we can observe all variables, but some samples may be missing. We define incomplete versions, corresponding masks. This paper, causal skeleton discovery from incomplete data, refers to the problem of inferring B from incomplete observation X. We do this by iteratively imputing X and updating B. imputing. Note that unlike previous causal discovery approaches dealing with missing data by either list-wise deletion or test-wise deletion, we aim to generate full observations and yield an optimistic estimation from X by imputation. Therefore, with X only, we then need to first recover underlying joint probability distribution from X and representing P and structure dependency among variables X. Okay, built on GAE and VAE, we generalized the work on Bayesian structural learning and proposed deep learning approaches to simultaneously perform missing data imputation, causal skeleton discovery. Our algorithm consists of components in generator G, a discriminator, a structure encoder, a structure decoder. Data imputation. Similarly, we use G and D together to approach the underlying data distribution for imputation, since GAN cannot take N values, not the number values, as input. To initialize the imputation process, we use the dimensional noise variable sample for generations and replaced not a number entries with X, where dot is element-wise multiplication. Okay, I'm sort of losing a little bit what's being said here. Skip a little bit and try to wrap up soon. Causal skeleton learning. Then we perform structure discovery to find underlying causal mechanism from the variable set V and X. Using structure discovery method in the U, with the scoring function SD, this concatenate task and turns into continuous optimization problem. Finding G that satisfies G equals to G argument minimum of SDG. Using structure discovery method with the scoring function SD is concatenated. Okay, so that structure discovery method is not apparently described here. That would be interesting. Causal direction identification. Above procedure can identify the conditional probability but may not truly represent the underlying causal mechanism. For example, given two variables xi and xj, their joint distribution can be decomposed equally as either these two decompositions relate to different causal mechanisms. With the additive noise model, these two decompositions relate to different causal mechanisms. With additive noise model, okay, however, we can represent asymmetries leading to unique causal direction from purely observational data. In detail, let joint distribution be the ground truth, then effect of xj condition on the cause can be represented by the above procedure can identify conditional probability but may not truly represent the underlying causal mechanism. For example, given two variables xi and xj, joint distribution can be decomposed equally. Alright. Okay, experimental results, baseline algorithms, quantitative results, synthetic data generation, missingness mechanism, quantitative experimental results. Okay, study conclusion. In this work, we address the problem of incomplete data causal discovery, and we proposed a deep learning model ICL to handle this issue. Specifically, our ICL model contains global view of iterative missing data imputation and causal skeleton discovery, and local view of enumerating causal directions to uncover underlying causal G. In the end, we evaluated effectiveness of our method on both synthetic data and real data. As future work, we will generalize our method under more complex conditions, such as existence of confounders. Okay, that's all. Thanks for listening, and maybe see you next time.